happy to welcome you at this seminar at SystemX, so which is a seminar series that we organize at IFT SystemX once a month, and we invite usually external speakers that we know, or that where we think their research is interesting or interesting to our interest or our field. And so today, my name is Jakob Puchinger. I'm the responsible of the Anthropologist Chair on Urban Mobility and also of the research axis on optimization and scientific computing at IFT SystemX. And so on behalf of the Direction Scientifique of IFT SystemX, I welcome you all to this seminar. And I'm very happy to have Anita Graser here. So Anita is a researcher in open source GIS or in movement data and she's also developing GIS tools. And she's working for the Austrian Institute of Technology in Vienna. We were colleagues there for a couple of years, and it was great to work with her. So I know her quite well. So thanks you, Anita, to be here with us. And Anita is very engaged in everything that is happening in the open source GIS world. So especially she works a lot with QGIS, and she teaches Python for QGIS at a university in Salzburg. And she also published several books on QGIS, including Learning QGIS and QGIS Map Design. And she also was awarded an award for her work at OSGeo in 2020, so last year. Recently, also Anita finished her PhD, so I think it must have been last week or 2 weeks ago. So congratulations on that. And also Anita is working on Moving Pandas. That is a Python library for analyzing movement data. And Anita is also very present on the social networks, especially on Twitter, also LinkedIn. And you can find a website of her also. I guess she will provide us the links at some point in her talk. So thank you very much, Anita, to be with us and to present on understanding movement data at our seminar. I'm very curious about your presentation.
Yeah, thanks so much, Jakob, for this kind introduction and for inviting me and having me here at your SystemX seminar. You already said almost everything, so there is not much need to continue this introduction. So most of my work over the last 10 years has been at the intersection between GI science, movement data, particularly continuously expanding massive movement data, and on the other side, on open source development, on open science, and trying to push the envelope in a direction where the tools that we are using for GI science and for movement data analysis are more open. And that's also why I started developing an open source library called Moving Pandas. And I'm involved in a lot of other open source projects such as QGIS or MobilityDB. And you can find a lot of news about all these projects always on my personal website, which is anitagraser.com. But today I want to talk about specifically movement data, and I want to talk about understanding it. And as a start, I have picked a couple of really, really neat examples of what you can do with movement data. And I'm sure you may have already seen one or the other example. Like here, this visualization of bicycle sharing system flows, which is really, really pretty. Or, for example, movement data from ships. And in this case, the different colors represent different ship types. So you can analyze which type of ship goes where, and you can see how fast they are moving, where it's particularly dense. You can see the main routes, all these kinds of things. And of course, there's also a lot of movement data from aerial vehicles. So flight information data makes for some really, really interesting projects. And that's also one of the few data sets that actually has very valuable 3D information, which is super challenging. So movement research itself is much, much larger than what I'm going to talk about to you today. So in movement research, a lot of researchers are really focusing on the movers or moving objects. They're focusing on understanding how a certain movement comes to pass. So why someone or something moves, how it decides which destination to go to, how it decides which route and which mode to choose. For humans, that is kind of obvious. We decide if we have to go to a certain destination, we may choose whether we want to walk, cycle, take a car, or any other vehicle. But also animals can choose different modes. For example, if you think of a bird, it might decide whether it's worth actually flying somewhere or if it can hop there as well without having to necessarily fly. And all these choices will be influenced by external factors, by the environment, by some restrictions that might be around. And in the end, there will be a realized movement path. So this is the actual movement that takes place once the mover has made his decisions. And once this path is being moved on, we can also track it. There are different tracking systems. Some of them are attached to the moving object, for example, a fitness tracker, and others could be remote, like a camera system that is following the movement of people or vehicles on the ground. So these different tracking systems then finally collect the movement data, which I want to talk about today. So the focus of this talk will be about understanding the movement data, how they are influenced by different problems with the tracking system, what you should be aware of, how you can start dealing with it. And today we will focus less on understanding the left side of this graphics, which is why people move, even though that's super interesting as well, but that's basically the cutoff of today's talk. And while we had some really nice visualizations in the beginning with these videos of bicycle sharing data, ships or airplanes, in the real world, it's not that pretty. If you get real world data, it's going to be more or less a nightmare. It always is. And that's because in movement data science, we see a lot of opportunistic reuse of data. What does that mean? Usually the data collection process is more or less undocumented or a black box. We use data that has been collected for other purposes. We may be using social media posts that have geotags attached to them. We might be using cell phone network data, which is actually just collected to make the cell phone network function and to provide bills to the clients. But they also, of course, gives us information about the location of the phone. So it can be used as movement data, and it is used as movement data a lot, as we have seen during COVID. Then there can be mobile apps which provide you GPS data from phones. Then there are dedicated vehicle tracking systems. Those are probably the closest to a system that was specifically built for the purpose of movement data collection. But even so, quite often these systems are built for daily operations, for example, for optimizing the distribution of vehicles in a city so that they can quickly service clients. They are usually not built to understand the bigger mobility system in an urban or even bigger regional setting. And the same is, of course, true for Wi-Fi tracking data, check-in data, or even payment data from, for example, credit card companies. All these data sets are valuable, but they are also usually biased and quite often messy. And the metadata records, as I already said, if they even exist, so if the documentation even exists, it's a sad story, but it's always incomplete because it's practically impossible to foresee all the future uses of data. So even if you try your best and try to write good documentation, we usually end up with something that is far from ideal. Another thing that's challenging when you think of movement data in general is that there are so many dimensions on which movement data vary. So some movement data will have particularly high spatial resolution, for example. If you imagine you're tracking something in a video image from a camera, then you can actually determine the position of, for example, a person pretty accurately down to a few centimeters of accuracy. If you have GPS tracks, you might have plus minus 10, 15 meters accuracy. If you're talking about data from cell phone networks, it might be kilometers in spatial accuracy. So spatial resolution is something that varies a lot. So do the spatial dimensions. Usually we get 2 dimensions, but I already mentioned in the airplane example that you might get 3 dimensions, and there are very few tools that actually support that so far. The temporal resolution and the sampling interval, they are kind of related. So that would be how often you get an update of the location. In many fitness trackers or GPS trackers, it's common to go in with a 1 Hertz sampling frequency. So you would get 1 precision per second. On the other end of the spectrum, for example, you might have only 1 precision per day if you get animal tracking data for monitoring migration routes of birds. They try to save battery life, so they only record very few positions, and they're interested in very large movement patterns, so they don't need more need to gather more information. So the sampling intervals can also be regular. Like I said, with 1 Hertz frequency, you get 1 position every second, but they might also be triggered by events and therefore be irregular. For example, if you think about geotagged tweets or other social media check-ins, you will get one whenever the user feels like, whenever they send a message. You cannot count on there being a message when you need one. Another thing that makes a difference for movement data is whether there are constraints and how they affect the movement. And the classical constraint would be if you have, for example, car movement. It usually happens on a road network. So you can do a lot of analysis by matching the movement of the car to a certain road network. And then you can say, for example, the average speed on this road network link is 50 kilometers per hour. Other movement like birds, flying in the air are not constrained, not at all, or only very limitedly by the, for example, topography, by mountains or other environmental factors. Other dimensions include the movement models that we are looking at and the tracking system. For example, the tracking system can be, as I already mentioned, attached to the mover, or it can be remote or checkpoint based. So if you have, for example, camera traps for monitoring whether animals visit a certain location, that would be a checkpoint based system. Also, if you are thinking of the cell phone network data, that is also every one of these antennas has a fixed location, and you can only pin down the location of a mover to this fixed location. So these are the differences in tracking system that you will encounter if you work with different movement data sets. Similarly, privacy can be a huge issue if you're talking human movement. It can even be an issue if you're talking animal movement. If you're dealing with endangered species, then it's quite likely that you do not want to publicly make available the location of these animals because you might be endangering them if you do. Other data sets are commonly available. For example, ship movement data is being broadcast for between ships and to coastal stations. And they exchange that because it makes the traffic safer on the sea. So it's a mandatory system that broadcasts location. And of course, finally, last but not least, when dealing with movement data, the data set size and the speed at which new data is generated will have a huge impact in which tools you can use, how you can analyze them, and in general, what your experience will be dealing with the data. So data science reality check number 1, data preparation is super time consuming. It's typically the most time consuming step. So if you are a data scientist, you certainly know. If you want to become one, then you should know. you will spend a lot of time massaging your data, preparing it for analysis, much more time than you spend on, for example, training machine learning models or making interesting visualizations. And what is it that you're doing in this whole process? For me, one of the most essential parts of this whole data preparation and data processing and making sure that the data is suitable for your analysis is exploratory data analysis. And exploratory data analysis is an essential part of this whole data collection, data processing and cleaning circle. Usually it goes back and forth. It's very iterative. You get a new data set or you collect a data set, you do your basic data pre-processing using the assumptions about the data characteristics that you currently have. And then you start looking at the results of your pre-processing steps. And in almost all cases, you will find out, okay, there's an issue that I have to look into. There, it looks like one of the sensors might have failed. Maybe we can collect more data at that location. And this pre-processing didn't really work the way I intended. And then you go into the next iteration. You collect more data, you do more data pre-processing and cleaning, and then you look at it again. That's normal, it happens to everyone, and you should plan enough time for that. And only once that is done, and you can go on to really doing, for example, confirmatory data analysis, the statistics, calculating the statistics that you need for your reports and for your data products. And one point I always want to stress is in exploratory data analysis, we need visual tools. You cannot rely purely on descriptive statistics. This animation is taken from an Autodesk publication and it's called the Datasaurus. And you can see on the left-hand side how the pattern is constantly changing and every human visually can recognize the dinosaur right now, the Datasaurus. While on the right-hand side, you see those descriptive aggregate statistics and they're not changing at all. So they wouldn't tell you what's actually going on the left-hand side. And this happens so often in many data sets that we encounter. It's simply not sufficient to just look at the numbers. We need to visualize this data and we need to visualize it in many different ways to find all the potential issues that a data set has. So movement data rarely collected in a lab setting. I already mentioned lots of different systems are being used to collect movement data. All of them are usually built for a different purpose, and that's why the data quality is not ideal. You will encounter tons of issues. I just want to show you a couple of them. For example, there might be missing areas or sections. For example, if someone pre-processed the data for you and they cut off a part that shouldn't have been cut off, then you will get these fragments where obviously data is missing. And if you would use, for example, derived information such as movement speed along this section, you would get very, very wrong results. You will also quite often encounter that there are location records which would not be anywhere on Earth or definitely are not within the area that you're expecting them to be. So for example, in ship movement data, it's quite common to get coordinate values that are way, way off because this data is transmitted via radio signals, and it's quite, it happens quite often that there is some transmission error and that results in wrong geometry coordinates. You can also have issues such as that multiple objects, multiple vehicles, multiple persons somehow get assigned the same identifier. So they both might be vehicle number one, but they are moving in different parts of your analysis area at the same time. And if you visualize a trajectory, a movement like this, you would see zigzagging lines like in this example. Of course, there's also a lot of measurement noise that's to be expected. Sometimes it's more extreme than one would expect, but these hairballs, bumbles, whatever you want to call them, at location where the moving object actually pretty much stayed still, are very common and have to be dealt with. Some movement tracking systems have even weirder issues. For example, you might receive the positions in the wrong order. So here you can see the different locations numbered, should be numbered through and increasing in the values, but some of them are just in the wrong order because the transmission time might be used as an actual sending time. Of course, you can also just have off-course positions or zigzag movements, either because the values of the coordinates were truncated or because of other pre-processing steps that might not have been documented well. And sometimes it's also just your experimental design. Like we once asked people to drive around a certain intersection to record how change in traffic light systems affected the waiting times at this intersection. But one of our participants didn't get the memo that he was expected to drive around. So you can see this guy here who's currently walking in the park. He seems to have picked up the GPS tracker, taken it out of the car and started going on a lunch break or whatever he was up to, maybe going for a smoke. So he had a nice break in the car with the GPS tracker, potentially confusing our analysis. And that's something that you can easily spot if you visualize your data. So exploratory data analysis is great to suggest hypotheses, also to assess assumptions. Like our assumption in the previous example was that everyone would be driving, which obviously was not the case. It also helps you to select the right statistical tools and techniques by showing you, okay, I thought, for example, that the data would be coming in regular intervals. Now my exploratory data analysis shows that there's a lot of irregularity in the temporal sampling. Then I have to use other tools. I have to either pre-process the data so that I get regular intervals, or I have to use methods that can deal with this complication. And of course, it also always informs further data collection, whether you do it for the current project or whether you keep it in mind for a future project. It will certainly help you improve your experimental design or just your requirements document for your data providers. How can you, if you start out in movement data science, how can you quickly assess a new data set? What I found was that there was really no guide. There were a couple of papers that specified what are common issues, but there was really no step-by-step tool, guideline, checklist that could be used to have a systematic approach and to not waste time while trying to get to the meat of the subject of actually doing work with the data. So what I developed is what I call an exploratory data analysis protocol, particularly for movement data and particularly well suited for continuous movement data like GPS tracking data. And it contains a number of different steps. The basic version is technology agnostic, so you can implement it with whatever tool you like. But there's also then an example implementation, which I will show you in a few moments. But first, let's go over what it covers. And of course, this now relates to the examples that we have seen before. There are 4 big categories of problems that this protocol will help you to discover. The first is the missing data problem. The second one is a precision problem. The third one is consistency problem. For example, whether the sampling interval is consistent or heterogeneous. And the last one is the accuracy problem. And to find these different problems, we have to look at different versions of the movement data, at differently processed movements. So with the original raw, what I call elementary records, which is just consists of the coordinates, the timestamp, and the object identifier in the minimum version, you can do a lot of missing data evaluation. But that's it. All the other problems can only be discovered if you process the data further. So if you generate segments, that means if you connect consecutive elementary records, then you can find out about gaps. You can find out if there's problems with coordinate or timestamp precision. as well as some of the consistency and accuracy problems. And for the last group of problems, you need to not just have the segments between consecutive records, but you need to build the overall trajectories. So you need to connect all the segments that belong to the same user to find out whether there are problems related to, for example, mover heterogeneity, tracker heterogeneity, or object identity, like the one zigzag example that I showed you before, where two objects were having the same identifier. So the open source reference implementation that I will show you now is also available on GitHub and on Zenodo. And it even includes the data, so you can run the whole thing on your own afterwards if you feel like it. But with that, let's go over to the live demonstration, to the Jupyter notebook. I hope you can see it. Let me know if that's not the case. You can see here, it's again the same for problem categories that we just talked about. The implementation is based on Python. So there's a lot of use of pandas, GeoPandas, and my library Moving Pandas, together with the visualization libraries that we need to do proper exploratory data analysis. And here in particularly, I'm using Data Shader and the whole views family. You will see in a moment what these tools provide in terms of visualization. The data that I'm working with is movement data from ships. So I have imported 2 days, one in July and one in January of ship movement data. It has a lot of different columns, including the object identifier called MMSI, as well as coordinates, latitude, longitude, different status information, speed over ground, course over ground, heading. All these kinds of things are very interesting to explore. One of the early things that I did for movement data analysis in this case is to remove all the records that have a movement speed over ground of 0, because that means there is no movement, and it's really a lot of records that you can throw away like that, and you don't have to bother with making your analysis faster. So in the end, I've narrowed it down to these couple of columns for the further analysis that you can see here. And we still have 10 million records in our data set. So it's not a small data set that you're dealing with here. But that makes it even more interesting because you can see a lot of things, and you can also see that the tools, they actually work pretty well, even with this size of data set on a pretty standard computer with 16 gigabytes of RAM. So we said missing data is the first one and the most simple problems to actually detect. If we look at spatial gaps and outliers, it's very helpful to do basic scatter plots like this one. And I have explicitly turned off the usual density map, heat map style, so that you can see each and every individual points, and you can actually see these outliers here at completely unrealistic locations, which we definitely have to clean. And you can see the much denser area of where there's actually proper coordinates available. And you can see how the data is being rendered. All the 10 million points are nicely rendering in this interactive map. So if you have big data sets, I heartily recommend these libraries. Here I do some basic cropping. So I remove all the latitude and longitude values that are completely unrealistic, or you can even crop it a bit more closely to just your area of interest. For example, here around Denmark, to see what's going on there. If you have eliminated those complete outliers, the next step in the missing data is to find out if there are any spatial gaps. So within our area where in general there is data available, there might still be certain locations where there is no data for whatever reason. With ship movement data, obviously we are expecting that there would be gaps on land. So there shouldn't be much movement data on land. There is some, which is the case because the AIS dataset also includes, for example, helicopters or rescue planes. So there is actually some data here. But there are also areas here that you can see which are pretty empty. Could be due to there actually being no traffic there, could be a protected area. Could also be that we just don't have sensors or antennas that cover this area properly, and that might be why we don't have data there. So it's worthwhile exploring the areas, the dense ones, the not so dense ones, and see if that matches with your assumptions. The same applies to temporal gaps and outliers. So since we only imported 2 days, one in July and one in January, of course, we have a large gap in between, and we have high peaks at the end of the overall time frame. It could have happened that there would be some other peaks in between. Those would have been interesting, but in this analysis, it's not the case. The dataset was clean in a temporal sense. We can also look, for example, into gaps within the days that we have data, for example, by hour of day. This visualization mostly tells us that in January, there are much fewer vessels moving around or contained in our data set than during summer, which also makes sense because in Denmark, there are a lot of sailors who are more active in the summer than in the winter, where the weather is just not nice enough to go out. Another thing that you could do is now combine the spatial and the temporal gaps, because some of the spatial gaps might just be temporary. Also, the extent can change from time to time. And in this case, there's an enormous difference between July and January, because for some reason, the data set in summer contained the North Atlantic and large areas of Northern Europe, while in January, suddenly the extent of the data set decreases to just the area around Denmark. And that was not documented anywhere. We only found that once we looked at the data. You can also look, of course, at different hours of the day, like 6 in the morning or later during the day, and how the ships are distributed. That might lead to the discovery of some patterns as well. Same with temporary gaps. For example, at midnight, here you will see that some of the ports are, of course, much less active. There's not much movement going on, while during the day, there's a lot of traffic going on. That actually makes sense, so this is not surprising. If that wouldn't be the case, there might be an error in the timestamps. You might be misinterpreting, for example, the time zone. And you might be thinking, okay, why is there so much movement at midnight? And that could be the case because the actual local time might be something in the afternoon or in the morning. So very helpful to look at that as well. There might also be gaps in attributes. I showed you before that there were so many different columns in the data set about speed, about status, about ship type. But quite often it can happen that a lot of these values are empty, are not provided. So you should also have a look whether actually these attributes are filled and whether they are filled everywhere. For example, in our data set, we noticed that there's quite a number of records where the ship type is unknown. And this seems to mostly affect the records that are located in the North Atlantic, while in the core area around Denmark, there is usually, we know the ship type here. Those are the gray ones. So there's definitely a difference in spatial distribution of the attribute information as well. So definitely worth looking at as well. After all these missing data analysis with the raw data records, this long section is about computing the segment information. So this code makes sure that you actually have segments that you can analyze to, for example, find gaps in trajectories. And the gap in this case is basically just a very long segment between consecutive locations. So if there's a long time without intermediate updates of the location, then we would call that a gap. And if we visualize these gaps, we can see that there is, for example, this one area here where a lot of these gaps seem to cluster. So probably we don't get enough, we don't have enough sensor coverage here, and we don't see where the ships are moving because of course they have to be moving somewhere here, but we cannot observe it. For the coordinate imprecision, that would mean, for example, if they are truncated too aggressively, if you would only have 2 digits after the comma, for example, for latitude, longitude values, then you would see specific values here, for example, 90 degrees or 45 degrees would be overrepresented in the histogram of directions of the segments between the consecutive records. In this case, there's nothing that sticks out too much, so most of this is fine. With the timestamp imprecision, it's very similar. So the most noteworthy thing here is if you get 2 records of the same moving object with the same timestamp, but with different coordinates. So the ship is at multiple locations at the same time. We actually do have a couple of cases where we even have 4 records at the same time. So that's worth looking into and cleaning up as well. For the consistency, for example, the sampling heterogeneity, we might be interested in how much time passes between consecutive intervals. And here we see it's mostly around 11 seconds update interval, but it ranges widely and it has a really long tail. So there are a couple of records over here with really long time differences, which makes sense because if a ship like leaves the area that is covered by our data set and returns 2 or 3 weeks later, then that will be the interval, 2 or 3 weeks. But in most cases, we get a really decent update frequency. We can also look at how much the location changes from one record to the next, and that is this coordinate change plot. So we always put the origin of a segment in the center of the plot, and then we plot where the next location would be relative to this one. And this, for example, can help you see if there is a pre-processing step implemented that might throw away all the information if the movement has not exceeded a certain distance. For example, you could imagine that you want to reduce data set size by making sure that there is at least 100 meters between the previous location and the next one when you send an update. And if that was the case, then you would get an empty hole in the middle of this plot. But since no such pre-processing was implemented for this data set, there is no hole. Actually, it's super dense in the middle here. For the mover heterogeneity, we might encounter cases where we are mixing different types of moving objects. For example, we could be expecting that all our data set contains our GPS tracks of cars. But in reality, like our guy who went for a stroll in the park, there are a couple of people in there who also recorded tracks with the bike or by walking or taking an e-scooter. So it's really worthwhile to also look into trying to determine whether you have, for example, consistency in the total daily distance traveled or the median speed traveled, or if there are any outliers which would indicate, for example, with the super high speeds up here, those are again our flying vehicles. They are not actually ships. And some of the vehicles that travel very, very far might also be of a different type, of a different kind, and definitely worth looking into. So I called the really fast ones speedsters, and I plotted them here on the map just to confirm that, yeah, they are also traveling over land, so they certainly have to be flying. Wouldn't make sense really otherwise. The long distance travelers, on the other hand, they are actually, they look like ships, but there's other problems related to those data sets. You can see these spikes here. So there are wrong coordinates here, which make the trajectory much, much longer than it was in reality. And yeah, that's also a really convenient way of finding these kinds of problems. And finally, I already told you some of the problems you can only spot if you have the whole trajectory. So we have to compute that, and this is taken care of in this piece of code. And with that, you have much more information that you can look at. You can, of course, look at the complete length of the trajectory, the median speeds, the overall duration, what accelerations are attained by the moving vehicles, or which direction it's moving. And if you plot all these things, for example, in this scatter matrix, you might spot some certain outliers that would be worth investigating and digging in deeper, finding out what's going wrong here, or maybe everything's fine and you just learned something new about your data set. So you might learn that some trackers have a certain sampling interval. For example, a lot of trackers here seem to be reporting every 20 seconds, while many others are reporting much faster, and some of them are clustered around even longer sampling intervals. So this could be due to different technologies used for tracking, for example. We can also look at the previously mentioned mover identity issues, such as non-unique IDs. So in this example, we have one super long trajectory over here, while all the other trajectories are much, much shorter. And that's actually one that I inserted for testing purposes because there was no such example in the data set. It's just called ID number 1. And I combined 2 previously existing trajectories to make this happen. And you can see it's basically the same zigzag that we had in the example previously given by the Andrienko paper. We could also have unstable IDs. That means that the identifiers of the objects are changing. They could be changing at a specific time of day or after every trip. So whenever, for example, in taxi data, you quite often see once the client is dropped off, then the ID of the trip will change so that you cannot identify which taxi did which trips. And in that case, you would see in a distribution of how long the average taxi trips, for example, are. In our data set, since I made trajectories that are exactly 1 day long, we see that all the durations, that most of the durations are 24 hours. And we, of course, also have shorter ones for ships that are not being observed for the whole day. So this is another sanity check that you can apply to your data set. We also already saw a couple of unrealistic jumps in the trajectories, so you can also find those if you look at the histograms of the speeds between consecutive records, because these jumps obviously will cause really, really high and unrealistic speed values. And with a Holo views, you can plot side by side, for example, these histograms as well as tabular information, which makes it easy to spot the IDs that you can then use to pick out a single trajectory and have that plotted like this one here, which actually just suffers from a single one of those wrong locations, but it's really, really far away. So that was very wrong, a very high speed value that was computed for this one. Other trajectories have multiple of those errors. So you can have a look at finding out exactly what's going on. Less obvious than these really high jumps is when there is a lot of noise in the GPS tracks. So for example, if you look at if the direction changes all the time between consecutive records, then that's an indicator of noise. And let me zoom in onto that one, which actually was flagged by this test. If you zoom in here, you can see that it jumps around all the time. It's not a very neat straight line like a ship actually travels. It's very jittery. And that's being flagged if we look at the direction differences between the consecutive segments. The same here, there's also a lot of zigzagging going on in this trajectory all over. So this one definitely has a lot of jitter. For another problem that we shortly talked about was the out of sequence position, where the timestamps are simply wrong, or that the order of the location in reality would have to be different. So here, the direction difference will be always close to 180 degrees because it's exactly in the opposite direction. And if we zoom in on one of those examples, then we can see this zigzag line where it's very clear that something went wrong with the timestamps here, and actually that the order of the positions should be different probably. or in this example, where there's a couple of segments with just very, very high speeds, which also indicates that they have been switched, the locations have been switched in this record. So this is the end of this notebook. This is a full run through that I gave you. If you want to try it yourself, it's all available on GitHub and on the Sonoro link that I provided in the presentation, and I hope that the slides can be shared with you as well. The datasets are available on Figshare, so give it a try. Try it with your own dataset, and I would be excited to hear what you learn from your own data. And with that, let me quickly go back to the slides. There are still a lot of challenges for working with movement data, not least about standardization of movement data and about how to represent it. You have now seen that we do a lot with individual location records, which are basically modeled as points usually. Then I was dealing with segments, which are just simple lines between a start and an end location. And then there were trajectories that are basically can have an arbitrary length and arbitrary number of records included in them. And so far, there's really not much standardization going on in the reference implementations. There's a lot of different solutions currently floating around. So that's one of the challenges that this area definitely faces. Also, while the notebook that I showed you now is very good for GPS tracking and data and similar continuous movement data, we still need exploratory data analysis tools for other types of movement data. For example, for the cell phone network data, where we have much larger spatial uncertainties, where we have much longer reporting intervals, and thus the challenges are of a different nature. We also need tools that help us identify bias in our movement data sets. This is really hard, and I hope to be able to look into that in the future more closely. Like, how can we actually find out whether and how our data set is biased towards a certain user group, towards a certain area, while another one is underrepresented. We also still have the challenge of data privacy. A lot of the visualizations that I now showed you, they identified individual vessels, individual moving objects. With the ships, that's perfectly fine because they are not private people. But if that was an individual, a person, and we would be looking at their home addresses and maybe where they spend their free time and where they work, we would certainly be breaching privacy. And there are currently no tools that I'm aware of that automatically warn you, for example, if you're about to do such a thing. And last but not least, many of the exploratory data analysis tools still need to become much more accessible to people. You will see a lot in the literature, tools that are demonstrated that are not actually publicly available. So I hope we can change that and make it easier to work with these kinds of data. If you want to find out more about it and also about how to deal with, for example, even larger moving data sets with not just a few million of records, but billions of records, I invite you to look into my other presentations from earlier this year, which you will also find on YouTube. And with that, I'm really looking forward to your question, discussion, whatever we are having now. Thank you.
Thanks a lot, Anita, for this really great and inspiring presentation, especially also with this nice demo, and you showed us how to use the tools, and as they are available as open source, this is really great, so everyone can use them. So for the discussion, I would suggest you to raise your hands, and then I give you the word for questions. Go on, George, please.
Hello, and thanks a lot, Anita, for your nice talk. I have a question. If you have two sources of data describing the same movement, are there some methods to do fusion and repair them using the two sources?
Yeah, that's an excellent point. So fusion from different sensor systems is still a very much unsolved issue, in my opinion. How to, for example, make sure which of the system takes precedence if they have contradictory information. That's something where there are no default tools and ways to handle that. If you have any pointers, I would really appreciate them for looking into this further, but I'm not aware of anything that I could recommend you for this particular challenge.
Okay, thank you. I don't have any pointer. Thank you.
Thank you, Georges, for your question. Is there another question for Anita?
Yes, I have a question. This is Fereshte.
Okay, thanks.
Sorry, I just didn't raise my hand because I didn't want to activate it in the Zoom.
Go on.
Yes, thank you, Anita, for the very interesting presentation. As someone who has worked with this visualization libraries, especially in Python, like Folions or GeoPandas, I think with what you presented that this library, the new library, is much faster in processing. Could you please correct me? And if you have any estimation of how much faster is this library? Because I have really problem in processing very large data sets and visualizing them in Folium or GeoPandas.
I can imagine. Folium is pretty limited. Folium is based on leaflet, and they're rendering all the individual points as vector points on top of the leaflet map. Therefore, you cannot put very many points onto it before it getting really, really slow. In contrast, the libraries that I've been using, particularly here, the data shader library. So here is the data shade is true command. That's the magic sauce that uses then data shade in the background, and they rasterize the representation of the individual points. If possible, they even use your GPU. So it will be running on your graphics processor in the background before it's being put into the notebook where you only see the resulting raster image. And that's why it's so fast. So definitely have a look into data shader and the whole of use library family. If you want to deal with or have to deal with large data sets that you have to visualize. The defaults that GeoPandas is currently using is Matplotlib, which is also quite fast, but of course then it's static. You only get static visualizations, which are not so useful for exploratory data analysis. And for really having geographic visualizations of data for lots of data points, I haven't found anything that would be faster than datasheet.
Thank you.
You're welcome.
Thanks, Fereshte. Are there any further questions? Anita, I have a question that is quite, I would say, more general. So when you do this exploratory movement data analysis, right? So you do this for a very specific data set, and then you analyze it, and then you look at it, and then you interpret it in some way. But what's the next step, right? So because then you might understand what happened, for example, in the last year in somewhere, but then will you move it towards something automatic, or can you then make maybe indicators that take use of this knowledge you had because you looked at the data and not only looked at some indicators? Can you maybe define new indicators? Maybe also for this dinosaur example, right? Is there, how do you go further then? What's your view on this? Yeah,
that's an excellent question. And I tried to touch a bit on it before on the motivating why we need exploratory data analysis for any kind of data set, really. It's because to pick the right analysis tools for a certain data set, you need to understand it. Otherwise, a lot of people who just dive in with their favorite tool, with their favorite analysis method, and try to apply it to a random data set, they will usually you get some results, but quite often it turns out they are not reliable, or only afterwards you find out, okay, I now mixed together, for example, tracking data that was reported at very dense sampling intervals and tracking data that was very sparse. And if you, for example, just do a regular heat map or a density map, basically mixing together those two things, you will completely overrepresent the more frequently sampled moving objects versus the ones which send you fewer data points because it's more sparsely sampled. So if you don't know about that, you will have a nice looking heat map, but it will give a completely wrong representation. So whenever all these tools, all these data sets that I'm analyzing is to avoid making these kinds of mistakes in our machine learning models, to have something that looks okay on the surface, but actually is not reliable if you really look into the details, because you missed something, and there's always something that you will miss if you don't do data exploration. So examples we did with the ship movement data was outlier detection in a very automatic way. So if suddenly a ship pops up in an area where there have been no ships observed before, or very few ships observed before, or if a ship moves at a speed that is completely uncharacteristic for a certain area, then we can raise a warning. So we have this machine learning model which exactly knows at a certain location for a certain type of ship, we're expecting this kind of behavior. And if we get a new record, we can compare it and we can say whether it's normal or not normal. And really to build these models and similar ones, we need to understand what we feed into the model. And I think that's the case even for very, very simple analysis like heat maps. Also from geography and from GI science, we know that the more densely sampled a line is, the longer it will get. So if you transfer that to movement data, if it gets longer, also the speeds increase. So even if you just calculate simple things like average speed for trajectories with different sampling intervals with different characteristics, you might get a bias just because of that simple relationship.
Okay, thank you for your answer, Anita. Are there further questions? No. So this, what you said here, this remembers me some work I was involved with when I was still at AIT. So it was, we did some routing algorithm for electric vehicles. Mm-hmm. And we were very happy. And the idea was that they don't use a lot of energy, right? So we did energy minimization. We were very happy because we found energy optimal or very low energy paths. But then we looked at the paths on a map, and then we saw that they were always going through the zones where there is a 30 km/h limit, and not through the roads where that have a 50 km/h limit, because for calculating the energy, we use the maximum speed on the roads. And of course, as the energy is less when you drive slower, we just took the slower roads. So I think that's an example where visualization was really the answer to some bad idea we had, or something we missed in just designing the algorithm. So I think also, and this is not data we collected, but this is data we created ourselves by an algorithm, right? So I think even in such cases, it's always good to have a look at what you do, actually. So
that's absolutely right. And you cannot overemphasize that at all. So looking really at every individual step in your processing chain and looking at intermediate results is so valuable in identifying issues, things that you just have not thought about, but that happen because of your algorithm, how you designed it, parameter choices that you made at some point. So you can avoid so many costly mistakes by just spending the time looking at your data and the intermediate results. Absolutely.
Okay. So is there any question from someone else? So if not, Anita, if there is some of our our colleagues that would get in touch with you or that want to use some of these libraries you described, I think they can reach you on, you put your contact data here.
Can reach me via mail, you can reach me via Twitter, or just go to my GitHub repositories. They're also all under my name, and you can leave a message there to find me.
So I know that some colleagues that were not able to follow your talk this afternoon because they are presenting at the conference. So I know 2 of them. And so they will watch your presentation as a video.
That's great. Yeah. So please also send me the YouTube link whenever it's ready.
Yes, we will do this. So if there is no questions left, then I would like to thank you a lot, Anita, for being with us and presenting your work. And maybe we can get you to come to Paris in person at some point and do something nice together in terms of research or collaboration.
That would be so great. Yeah, I hope it will be possible soon again to actually do those things, to see each other in person and not just remotely. Even though this was really nice, but in person, spending a couple of days and maybe setting up a joint project, that would be really exciting for me as well. Yeah.
Great.
Jakob, I think I have one question. It's Abdeladi.
Yeah. Okay, go on.
Yeah, so it's not completely my scope, but I'm just wondering as a general question. We know that it depends on the inputs that we have and the data structure or the features that we prepare. If in case we have different features as the one that you take as an input in your notebook. So in preference from your point of view, is it preferred to prepare the data set to be as close to the one as you take as an example, to be maybe faster in the exploration of the data? Or at least maybe take just the guidelines or the best practices that you provide in the different sections, and of course we have to adapt the code and to explore in another way.
Yeah, that's a very good question. Thanks. I guess it depends a bit on how different your data set is. So if it's not too much hassle to bring it into the same format of object identifier, timestamps, XY coordinates, then I think I would take the step to just change the data set, pre-process it, and it fits, and you can use the rest of the code as it is. But if the data set has different characteristics, for example, if you're talking about mobile phone data, mobile phone network data, then you will probably want to anyway change some of the analysis quite significantly, and then it may also make sense to just use the conceptual part of the protocol and do the implementation more independently.
Okay, thank you very much.
Welcome.
Okay, so if there is no further question, then I would like to thank you again, Anita, and thank everyone for being here with us. And don't hesitate to check out the SystemX website and Twitter feed for the upcoming seminars